Well, howdy there, Internet students. This is Mr. Hermanson. Today we're going to talk about looking at the constant differences between the terms in a table to decide whether a table is linear and also to help us write a rule or an equation for a table of values. So look at table 1 and table 2, table 3, table 4. And just look at the values and guess whether or not they're linear. So just go through and write yes or no for each. And then when you come back, we'll talk about that, how you can tell for sure. All right, so if you got them right, awesome, good job. So the first 3 tables are linear, the last one is not. And the way you tell is by looking at the difference between the numbers. Check this out. On the bottom here, every number goes up by 3, and every number on the top goes up by 1. Second table, every number on the output goes up by 5. By the way, the output would be the y values. And the inputs go up by 1. On this one, the outputs are going down by 2, which is fine, while the inputs go up by 1. And what I'm doing to get those numbers is just subtracting the numbers. On the last table, while the inputs are going up by 1 every time, the outputs are changing. First output goes up by 5, the second one goes up by 6, the third one goes up by 7. To be a linear relationship, you have to have both the input and the output going up by the same amount. At least that's one way to tell. Now, let's also talk about writing a rule for these. So if you take this plus 3 on the output, that's your rise. Output is your y values. Input are your x values. That's your rise, and if you look at the difference between the x values, that would be your run. So your slope is your rise over run, which in this case would be 3 over 1. When you write an equation, that's your coefficient. So it's y equals 3 times x plus something. Okay. Now, there's a couple ways you could figure out this extra part here. I just like to take one of the values, one of the inputs, like let's take this 1. Multiply that by 3. 3 times 1 is 3. And then I figure, what do I have to add to that to make it equal the output 4? That's what y is. And so that would be just adding 1 to the output. Okay. Now, I'll show you another way to do it. On the second table, it's a little bit easier. So there's your rule, 3x plus 1. And that'll work for anything on here, like I'll just show you here. If you take 3 times 4, that's 12, plus 1 is 13. That gives you the output, y. Okay, on the second one, we're going to say y equals 5 times, well, our slope is, remember this is our rise, this is our run. So our slope is 5 over 1, which is 5. So it's y equals 5x. And remember that this thing we add is our y-intercept. If that's in the table, which it is right here, because the y-intercept is right in the middle of the graph where the input is 0, so that output of 1 goes here. Okay? On table 3, our slope is negative 2 over 1. So we're going to write y equals negative 2x. And then our y-intercept right there is 0. So there is actually one other way you can find that y-intercept, like in the first problem here. We don't have a 0 in our input, but you could imagine what 1 is and just follow the pattern. If we go from 10 to 7 to 4, as I go from 3 to 2 to 1, then when I get to 0, I just need to subtract 3 more, and that would equal 1, which is that number right there. All right. Now the last table is not linear, so we're not going to worry about writing the equation for that yet. All right. Um, so we're going to use this thing called the method of constant differences to decide whether or not a table is linear. And what that means basically is that your rise over your run always has to be the same. Sometimes the tables will be messed up. Like, in fact, I'm going to do one of those right now with you first. See how the inputs here are all messed up? So if I find the constant difference here, so from 15 to 25 is going up 10. I'm not going to put a plus if it's a positive difference between the numbers, but so this goes up by 10 again, by 10 again, by 10 again. But my outputs are going down 1, up 4, down 1. So my rise over run is not the same for all of these. My rise over run right here is 10 over negative 1, 10 over negative 1, 10 over 4, 10 over negative 1. So that means I don't have a constant rate of increase. So we're going to say that that is not linear. Okay? And then we're not going to worry about the rule. Okay? I'll do one more with you and then I'll let you try the other ones. For this one right here, number 1, these numbers are going up by 10. The difference between them is always 10. And these numbers are always going up by 1. The difference between them is always 1. So the rise over run, the ratio of rise over run is always the same. It's 10 over 1. So my rule is 10 over 1 is my slope, which is 10. So my rule is going to be y equals 10 times x. And then to finish this rule out, I need this value right here, the y-intercept. So I'm going to put plus 3. Now, and the other way you can do it, remember, is just take this 10 times some x, like maybe this one. 10 times 6 is 60. You can see we would have to add 3 to that to make it equal 63. So this rule makes sense. All right, you try the second and fourth table, see if you can figure out whether it's linear or not, and if it is linear, what is the rule, like I just did there. All right, on table 2, even though the numbers seem to jump around a little bit, if you take the ratio of the rise over the run, like 18 over 2, negative 9 over negative 1, you always get the same number, and it's 9. So, so yes, it's linear. 9 is your coefficient of this equation, 9 times x. And then the y-intercept is in the table right there at the 0. So it's y equals 9x minus 2. You might want to check that equation, just make sure it works. If you take 9 times 3, that's 27. Minus 2 is 25. That works. Okay. And this one is, the outputs are going down by a half. The inputs are going up by 1 each time. So it's definitely linear. And if you divide those two, you just get this number, negative 0.5. And there's the y-intercept. This is actually a direct variation. It starts at 0, 0. And the slope is negative 0.5. All right. Another way you can tell if a situation is linear or not is by graphing it. And let's go back and grab that table that we just did that we decided was nonlinear. And we'll graph some of those points and just see what happens. So that's this table. I'm just going to make a quick snip of that and move it to the next page. All right. So let's just graph the points we can, and we'll show that they are not lining up. They're not making linear. So, whoa, that's going to be kind of hard, isn't it? Here's what we'll do. It looks like we need outputs of numbers that are always in the 5. So let's use a scale of 5 on our output axis, which is y. So basically what I'm saying is this is going to be 10, 20, 30, and so on. So I'm going by 5s. All right, so then, but on my x-axis, I'll go by 1s. So I have a point 135, that'd be right there. 225 would be right there. Those ones kind of line up. 315, that one lines up pretty good with those. So, gal, it's looking linear. And then we have 545, that's right here. Now we can see it's nonlinear. And 455, that's like way up here. So now you can see that these dots aren't lining up. Okay? All right. So you guys, in these tables, what we're going to do is we're going to look at the pattern and see if we can predict what the missing numbers are. I'm going to just let you do this. It'd be fun if you can figure out what the pattern is and what the missing numbers are. And then you can check back and we'll talk about how you found those. But basically, you want to look at the difference between the numbers to help you do that. All right, so here's the numbers I got. And on a couple of these that are a little more difficult where the pattern kind of is weird, like on number 10, I'll show you what I'm doing here. So this is going up 10, and this is going up 2. This is going up 5 for every 1. Now there's what I can use to continue the pattern. This goes up 20 for 4. These ratios are all the same, 10 over 2, 5 over 1, 20 over 4. They're all equal to 5. So this goes up 1. This goes up 1. I want to follow this pattern and add 5. Okay? All right. On this one, number 11, I noticed that these are all going up by 1. That's cool. Makes that easy. But these are not. This one's going up by 2, then 3, then 4, then 5. So the ratios are not the same. 3 over 1, 4 over 1, 5 over 1. So this follows a little bit different pattern. Okay? Now, in which of these tables do these differences tell that they could be linear? Go ahead and just write yes or no for linear on all the ones you think are linear. All right. So so this one is not because like this goes up by 1, this goes up by 1, this goes up by 2, this goes up by 1. Already you can see these ratios are not the same. So that's not. These ratios all are the same, even though the numbers seem to be going up by different amounts. When you divide the rise by the run, you always get 5. Okay, this is a no. We talked about that earlier, that those ratios are all different. This is a yes. These are all going down by 1.5, and these are all going up by 1. So yeah, that one definitely is. And this one is, these are all going down 4 every time. These are all going up 2, so all the ratios are negative 4 over 2. Okay. Now, if you wanted to write the equation for this last one, so negative 4 over 2 is your rate of increase. We're going to simplify that to negative 2. That'll be our coefficient, so negative 2x. And then we have to figure out what the 0 value is. It would actually be right here. Okay, now which is halfway between these two. So it's the number halfway between these two, which is negative 4. That'd be one way to get it. The other way is just take a value, like maybe 5 times negative 2, because that's what we're saying we're doing here. And 5 times negative 2 is negative 10. You would have to subtract 4 to make it equal the output, which is negative 14. All right, that's all I got for you today. You're going to do for today the next page. Do it, so go ahead and do page 6, and then you're going to submit those answers on the Google form. All right, good luck with that, and we'll talk to you soon.